So there's a good chance I have a bit too much content, so I'm just going to jump right in. So as cartographers, we're constantly trying to wrangle data from a wide variety of sources. And one of the sources that intimidated me the most before starting at Planet was raster data, and specifically satellite imagery. Today, I'm hoping I can do a bit to demystify some basics and provide solutions for a few gotchas that still trip me up to this day. Just for clarification, I'm going to focus on data that's been collected by Earth imaging satellites. I acknowledge there's a lot of other sources of remotely sensed data, and they'll share many characteristics and caveats to the data sources I discuss here. I'm also going to focus specifically on passive sensors, as different techniques are needed to analyze active sensors such as LiDAR. So my goal here is to break down two questions. One, what do I need to know in order to use this data in a map? And two, what are new maps that I could make with this data? Although the answer to that second question is really up to you. So I'm going to examine imagery using in 4 different aspects of it. By looking at spectral resolution, radiometric resolution, spatial resolution, and temporal resolution. And I'm going to define each of these as we go. So first, spectral resolution. So I'm sorry, I'm getting a notification that I've been muted.
I think that was your other, sorry about that, your other connection to the green room. You're good.
I'm good. Okay, I'm gonna keep going. I'm sorry. Yeah, so it's spectral resolution. This is the number and dimension, i.e. the size of specific wavelength intervals. So you might be thinking, what do wavelengths have to do with it? I'm used to thinking about satellite imagery in terms of bands. So a band is just a specified wavelength interval in the electromagnetic spectrum. So what I'm showing here are the spectral responses for some different satellite constellations at different intervals across the visible and near infrared portion of the spectrum. So there's a good amount of variation between different systems consider a band, and even variation between the size and slice of the spectrum that's being collected depending on the system. So for example, you'll notice that GOES doesn't have a visible green band, while MODIS has 3. So sort of a tip here is when creating an image composite, it's important to double check and make sure the bands that you're using are the recommended ones for the task. There's a bunch of different characteristics between bands other than their location on the spectrum. So if there's 3 NIR bands, that doesn't mean they're all interchangeable. There's also a huge portion of the electromagnetic spectrum outside of the visible range that can provide lots of insight about our planet that we can't see with our naked eye. So for example, here, the sort of mid-infrared spectrum. It's also noticeable that different constellations vary in the portion of the spectrum that they image and the number of bands that they have. So for example, Sentinel-2 doesn't have thermal bands. Meanwhile, MODIS has 36 bands in total. So in the thermal infrared portion of the spectrum, MODIS bands can be used to measure everything from atmospheric temperature to ozone. I do want to note that Landsat does have thermal bands, but they're on a different sensor and I did not include them here. So now that we know where in the electromagnetic spectrum different sensors are collecting information, let's look at how different materials are reflecting in some of those ranges. Different materials can vary really widely. And so those spectral differences are useful for identifying how to identify them, and therefore we can use different like band indices to identify specific features in an image. These characteristics also become easier to see in color composite imagery. So basically these different responses answer that, like, how do they know of remote sensing indices? So for example, you can see that coastal seawater absorbs a lot of light and it's extremely dark except for the slight bump that you get in the like blue-green portion of the spectrum. Whereas grass is also fairly dark in the visible, but it starts to get a lot more reflective in the near and middle infrared. So let's look at what these actually look like as an image. So this is a subset of Sentinel-2 bands showing varying reflectance in the same area in different bands. So basically, the brighter a pixel is, the higher the response. So for example, you can see that healthy vegetation is bright in the near infrared, which is reflective because the amount of water and healthy plants. But you can also see that newly burned land, for example, is really reflective in the shortwave infrared. So just a heads up, sometimes a sensor can actually saturate in a given band. And in this case, a pixel will appear pure white. And that's kind of like, it's basically your data is clipped. So let's look at a true color image of Santa Cruz. You can see downtown Santa Cruz is visible in the far right corner along the water, and then part of the burn scar from the lightning complex fire earlier this summer is visible in the upper left. Let's look at it in a different band combination. This is a pretty common false color combination using the near infrared red and the green. This combination actually, at least in my work, has become shorthand for false color imagery because of the prevalence of RGB and near infrared bands across different remote sensing systems. It's also noticeable how dark the water becomes when we remove the blue band. Sort of a quick tip is the atmosphere causes a lot of interference in wavelengths. And so when you're color correcting a true color imagery, one of the first steps is going to be to remove a lot of blue. This band combination is great for showing healthy versus unhealthy vegetation, but it's possible to get more contrast in other combinations. It's also useful for detecting burn scars, showing where recently burned land appears darker than bare ground. So in this combination, using the shortwave infrared, near infrared, and green, you can see that recently burned areas appear more red and darker than bare ground, which makes them easier to distinguish than in the NRG combo. Plant health is also easier to discern because in the green band, using the near infrared, it's almost like electric green because of how reflective it is. I also wanted to say this is a good example of where I got caught compositing different bands without checking their spatial resolution first. In Sentinel, the near infrared and green bands are 10 meters, but the sphere band is 20. And so when I composited them, the pixels did not align perfectly. One way to address this is using GDAL's resolution lowest flag, which would resample everything automatically to 20 meters. Some things I'm not going over today, but just to be aware of when you're making your own maps, is band math and using different remote sensing indices, for things like NDVI, can be super useful here just by combining and doing math on different bands. One of my favorites is using NDWI, which is a norm water index, and using that to create a water mask. Oops. So next is radiometric resolution. Radiometric resolution is commonly expressed as a bit number, often 8 or 16 bit. This is the range of potential values that can be contained within each pixel. So many satellite sensors are actually 11 or 12 bits that are then resampled to 16 bits. So this means that while the potential values contained within each pixel in an image range between 0 and 496, or 4096, sorry, the image you download will have a pixel which could range in value between 0 and 65,536. So basically what this means is when you open up a satellite image, either in your default image viewer or if you open it in Photoshop, it's going to appear super dark, almost black, because all of the data is contained in the very low end of the histogram if automatic stretching is not applied. So as a tip, you can again use GDAL, this time using the scale flag in GDAL Translate to sort of stretch those values, so sort of resample the image, which can help with histogram stretching down the road, especially if you're trying to create a color corrected image. Okay, great. I thought I turned off my Slack notifications. So let's just look at what bit depth actually means in a visible image. Especially this becomes super important when you're saving and just image size. So for example, a binary image, an image that contains only zeros or ones, will be smaller than a single band 8-bit image, which will again be smaller than a band color 8-bit image. And so as we know, an image can have any number of bands. So decisions that you make about radiometric resolution are compounded as you add more bands to your image. So when you're saving a file, you need to be really aware of, is it 16-bit, is it 8-bit, could I resample it? All of that information, just to kind of save your hard drive. So for a color corrected image that you're using for a base map, think a true color base map, or maybe a hillshade even, 8 bits is often more than enough after you've done all your correction in order to create an image that really doesn't have a lot of visible reduction in image quality. I'm also not going to cover this here, but like the compression that you choose to use can have a huge impact on file size. I tend to use LDW when I'm saving out using either Photoshop or GDAL. Bit depth is also super important when creating GIFs, so feel free to Slack me if you're creating a lot of GIFs. I have tips. Next is spatial resolution, and I think when we talk about resolution, this is what a lot of us think of. This is the smallest size of discernible features within an image. So some influencing factors on spatial resolution can include both the sensor as well as the height of the satellite orbit. Typically, the further away the satellite is from Earth, the coarser the resolution. So for example, looking at a comparison of a 0.6 meter image, it's possible to discern logs on a log flume ride because those log boats are somewhere between 1 and 2 pixels wide. But when you resample that same image to 1 meter, you can no longer discern the logs. So sort of something to keep in mind is that it's possible to take away information from an image by resampling, but you can't add information. So here I've resampled the Sentinel-2 image to the same resolution as the 0.6 meter NABE image, but no beach blankets have mysteriously appeared. Pan sharpening is an exception to this process where it is possible to add information by resampling lower resolution bands to match a single higher resolution pan band. And I just wanted to give a shout out to Josh Stevens for an excellent blog post about how to actually do this in Photoshop that I found while researching. So if you want to learn more about pan sharpening, maybe start there. But also don't fall into the trap of thinking that more pixels are always better. Instead, aim to choose a sensor that's an appropriate resolution for the problem you're trying to solve. So if you're trying to build a machine learning algorithm that determines when beaches are busiest, you probably need sub-meter imagery. But if you want to identify ocean versus beach versus urban, 10 or 30 meters might be more than enough. So if you have some flexibility with which sensor you use, you can always download an image with a slightly higher spatial resolution than you need, and then downsample to a resolution that's appropriate for your map. And in the end, you'll probably have a slightly sharper, more appropriate base to your map. And finally, we have temporal resolution. This is how often a sensor records imagery of an area. So different phenomena have different temporal resolutions, and how often there's a usable image of a place can depend on how frequently the satellite is passing over and also clouds. So currently Landsat, which you can see in this graphic here, is revisiting a place on Earth approximately every 16 days. Whereas Sentinel-2, if you include both A and B, will revisit the same location about every 5 days. Or a satellite like GOES in a geostationary orbit, it's going to revisit every 15 minutes over the continental US. But it's also going to have 1 kilometer pixels versus 30 or 10 meters. So typically, as like a rule of thumb, the higher the latitude, the lower the spatial resolution, or the higher the spatial resolution, the lower the revisit time, but this rule of thumb can change depending on the number of satellites in the constellation. Latitude also plays an important role. So at higher latitudes, the swath widths can overlap for an increased revisit rate, but the viewing angles might be slightly different. So this means if you're looking at an image at a higher latitude, you potentially have like more options to choose from, but there could be differences in how shadows appear that could make hard to like mosaic images from different days. The ability to task a satellite, so pointing it using some sort of onboard propulsion to capture a particular location is another way that you can alter temporal resolution. So for example, in my work, Planet SkySats have a theoretical revisit, these are our high-res satellite, theoretical revisit rate of multiple times of a high resolution collect in a day, but that's only if an AOI has been tasked. Otherwise, there can be locations on Earth that have never been imaged by that sensor. So as a tip, when you're choosing a constellation for your map, think about how often that imagery is collected and how frequently you need the imagery. And also make sure that you pay attention to the collection time, since it can impact how colors appear. So it seems at noon it'll be really bright, or if it's collected early in the morning, it might have long shadows. So let's put this all together. I really love this graphic. It plots spatial resolution versus temporal resolution in sort of different uses for different systems. So implicit in the graphic is the spectral resolution that makes that system appropriate for each application. It's an older graphic, it doesn't have every system, but I really like it as like a gut check. So for example, Are you trying to monitor a fire using Landsat? You might miss it due to the temporal resolution, but if you're trying to show the impact of the derecho in Iowa this summer on crops, you might be right on the money. So yeah, I hope this got everyone thinking about ways to employ satellite imagery in their work. It was a bit of a crash course, so reach out if you have any questions and I'd be happy to help.